thank you very much for the invitation. It's my great pleasure to be here in Chennai and to visit India. So as the title of this lecture of series, I gave analysis and geometry on groups, which is very general analysis. And, well, more precisely, the topics which we'll treat in detail concern two properties of which are interesting for infinite groups. So it's amenability and property T, which play a very important role in the study of groups from the point of analytic, geometric, also representation theory. We will see that these are two really fundamental properties to understand the world of infinite, say, countable groups. However, they both of them have very interesting analogs among finite groups. But in this case, it's more about not just one, but a family of finite groups which are quotients of a given infinite group, and in particular will be concerned with so-called expanders graphs, which play a role in also not only in mathematics but computer science, and I'll also maybe mention some recent applications to operator algebras. And as actually talking about, so we'll be really mainly dealing with infinite groups, and then with this very interesting application to the finite quotients. But before giving you, reminding you of the definition of these two notions, let me say that they are really opposite. Okay, as far as infinite groups are concerned, ideally, actually, one would like to divide the world of infinite groups along the groups which have property similar to property T, and along amenability property. So, right, if a group is amenable and has property T, it's necessarily a finite group. Okay, and actually in June in Paris there was conference dedicated to Margulis' 70th birthday of Margulis, and who work a lot about these properties. Actually, many Indian mathematicians attended this conference because it's a very, very strong subject in India. And Margulis gave a talk, kind of autobiographical talk about mathematics he did. And he did many things, of course, but in his talk he said that he thinks that his best theorem is a so-called normal subgroup theorem, okay? Well, which says, for instance, that that non-trivial quotients of a group like SL3Z are necessarily finite. And it's amazing that in order to prove that some groups are finite, he really used these two properties, which are interesting only for infinite groups, amenability and property T. So by showing that these groups have these properties which are completely opposite in the world of infinite groups, he proved in this way that they are finite. Okay, so although these properties we'll study them for infinite groups, that's where they're really interesting. We'll see also surprising consequences as far as finite groups are concerned. Okay, great. So let me start by reminding you a definition of amenable groups, which goes back to von Neumann. So it's one of his first papers from 20s. So we say that a group gamma is amenable if there exists a mean, so a measure, probability measure defined on all subsets of this group, okay, probability, which means, well, so it's in values 0, 1, such that, well, it's a measure, so measure of the union, it's finitely additive, is the sum measures, okay, so for all subsets of gamma, okay, which are disjoint, the normalization is that the measure of the whole group should be equal to 1. And the third condition, which is the most important one, is that this measure should be invariant by translations. Okay, say left translations, so that the mu of gamma A is equal to mu of A, and this is true for all subsets in gamma and all elements gamma in the group. Okay, so that's the original definition of amenability as it appeared in the paper of von Neumann. Okay, so maybe an obvious remark is that in the case of finite groups, it's not so interesting. So if gamma is finite, this mu it's easy to see that it's necessary the normalized size of the subset A. So that the mu of A is the size of the subset divided by the cardinality of the group. Okay, so we will see that interesting things happen for infinite groups. Okay, the origin of this notion, so it's the paradoxical decomposition of the sphere. So let me remind you Banach-Tarski paradox. So it's much more general, but let us see it for the in the simplest case of two-dimensional sphere. Okay, so it says the following thing, that the two-dimensional sphere can be represented as a union of a finite number of disjoint subsets. I think 8 will do, but it's an exercise for you to check it. So S2, two-dimensional sphere, is a disjoint union of 8 subsets, which we'll call A1, A4, B1, B4, and rotating using rotations out of these 8 subsets, we can actually get 2 copies of the same sphere. So then there exists 8 rotations, H1, H4, G1, G4, so elements in SO3, okay, rotations of S2, such that S2 is a disjoint union of rotations of the first 4 subsets. So H1 of A, disjoint union H4, and also S2 is the disjoint union for G1, B1, disjoint union with G4 to B4. Okay, so it's clear that, yes? So you're saying that I could do it with 4, not 8? Yes. Yes, so here I take first 4, and here I take the remaining 4. Okay, so out of these pieces, actually we can get 2 copies, okay, of the same sphere. Okay, so as you can imagine, immediately this theorem became very popular, and of course the subsets are not measurable. Okay. Pardon? Yes, all these are disjoint. And is it the standard notation? Okay, I will. Okay. With the dot? Still with the dot. Okay. Very good. Right. Yeah, it's important. It's disjoint. Okay, and it's called Banach-Tarski paradox. Okay, so right. So if we had a measure, well, not Lebesgue measure, but another measure on S2, which would be just finitely additive, not necessarily sigma additive, but finitely additive, and invariant under rotations, this would certainly prevent us from having this this paradoxical decomposition. So existence of such a measure is an abstraction to this, and actually we will see it's the only abstraction. Okay, and like from the historic perspective, it should be said that, well, the Lebesgue measure, this beginning of 20th century, I think it's 1901, I think. So at the time, essentially, everything was understood about sigma additive measure, and remember from the construction that one cannot define such a measure for all subsets. Okay, there is whole work to define measurable subsets, and then the interest shifted, motivated by this paradox, to just finitely additive measures. Okay, again invariant under groups of isometries, which could be defined on all subsets. Okay. And today we'll see that, for instance, one cannot obtain such a decomposition for S1, for the circle, because in this case we'll prove the existence of finitely additive measure invariant under rotations and defined for all subsets for the circle of the circle. Okay, so right. Let us now move to examples concerning this von Neumann definition of amenability. So the first thing, maybe we're going to see an example of a group which is not amenable. Okay, example of a group which is not amenable and which is closely related to this the composition of the sphere. So we'll consider a free group of rank 2, F2. So these are elements of this group are irreducible words, free irreducible words on the letters A and B and the inverses. And freely irreducible, it means that you cannot have a letter and followed by its inverse. So this and also B inverse B, these are forbidden subwords. Okay, so let us see that the group F2 is not amenable. That on F2 there is no finitely additive measure defined on all subsets, which is invariant under translations. Okay, so let us consider a subset of A2 consisting A plus consisting of words which start with A. So these are irreducible words starting with A. Okay, and similarly R minus, let it be the subset of words starting with A inverse. And in similar way, we define B plus and B minus as words starting with B and with B inverse. Okay, very well. So F2 elements of 2 are either words which start with A or with A inverse or B inverse, and there is also an empty word, okay, which is the identity, which plays the role of the identity this group, so plus identity. Okay. Now let us analyze what happens with the subset A plus if we multiply on the left of all words in this subset by A inverse. Okay, so we take, well, if we take a word which starts with A and we multiply it by A inverse, we cancel this A. Okay, so what can be, what letters can we obtain, can we have, what words have when we cancel the first A? Okay, so after A, we could have anything except A inverse. Okay, because this is forbidden to have a letter and its inverse. So this is the subset of words, arbitrary words, except the words which start with A inverse. So actually, if we add A minus, we obtain in this way all elements in F2. And in similar way, F2 can be a disjoint union of B plus translated by B inverse plus B minus. Okay, and what we have here, it's in a sense paradoxical decomposition of F2, okay, which we represented as the disjoint union of finite number of subsets, and out of the subsets, using translations, we can obtain 2 copies of F2. Okay, so indeed, if so, what is the proof of the fact that F2 is non-amenable? If it were amenable, so suppose F2 is amenable, then we have this measure mu such that the measure of the whole group F2 is 1. Okay, it is finitely additive. So from this property, it would be the sum of mu A plus mu of A minus, okay, plus mu of B plus mu of B minus and plus mu of identity. Okay. Now, using the fact that this measure is invariant under left translations, we can multiply this subset by A inverse, and the measure won't change. And in similar way, this one by B inverse, and the measure won't change either. Okay, and now using again the fact that it is a finitely additive measure, we can write that this is equal to the mu of the union of these 2 subsets is F2. The union of these 2 subsets is F2 again, and well, the measure of identity, well, it's non-negative, so it's greater or equal to 1. Actually, it's easy to see that the measure of the of the single element has to be 0 if the group is infinite. But anyway, we obtain that 1 is greater or equal to 2. Okay, and that's the contradiction. Actually, this paradoxical decomposition of F2, which we just seen, is used to get to obtain this paradoxical decomposition of the of the sphere S2. The way one does it is to realize that one can find a free subgroup F2 in the group of isometries, of rotations of two-dimensional sphere, okay, SO3. There are several ways to do it. Actually, if one takes two rotations at random, there won't be any non-trivial relation between them, and they will generate F2. But one can also explicitly write two rotations and give an elementary proof that they generate free group F2. Okay, so if these two isometries would act freely without fixed point on S2, one could simply induce this paradoxical decomposition of F2 onto paradoxical decomposition of S2. Okay, the only problem is that there are fixed points. So rotations have two. Each rotation has two. Non-trivial rotation has two fixed points, and that's why one has to use more pieces in this paradoxical decomposition. But essentially, you've seen how it's done. Okay, and right. So maybe if you really, if you want to understand what is the right number of pieces, first of all, you should this decomposition of F2, you should do it just with 4 pieces. Okay. There is a way to modify it to have not 5 but only 4 pieces, and right, and then it's easy to see that how one can deal with this set of fixed points, which is just countable. Okay, great. So that's an example F2 of a group which is non-amenable. Actually, one can it's easy to see, so that in this way we get many examples of, from this we can get many examples of groups which are not amenable. So another remark is that actually every group which contains F2 is not amenable. Okay, so many linear groups like SL3Z and so on are non-amenable, and the reason is very simple. Well, if you have paradoxical decomposition for a subgroup, you can induce it for the whole group, okay, with the same number of pieces in this paradoxical decomposition. And actually, having this paradoxical decomposition is the only obstacle to be amenable. Okay? So the group is non-amenable if and only if it admits a paradoxical decomposition. However, it's not true that the number of pieces should be, the minimal number of pieces should be always 4. Okay? It's 4 if and only if the group contains F2. And it's a very interesting question to ask whether there are other groups, non-amenable groups, which, if there are non-amenable groups which do not contain F2. Okay? And it led to very deep, I would say, developments in the group theory. Constructing such groups is not easy. Okay, actually, right. Maybe later I'll give you such examples. So maybe you will see that writing them is not so writing down them it's not so difficult. However, explaining that indeed they are not amenable is not it's not easy. Okay, so maybe now we'll move to examples of amenable groups which are not finite. Are there any questions concerning this part? Okay, so actually the simplest example of infinite group is amenable. So the theorem, which goes back to Banach, also from 20s, the group of integers is amenable. And let us see the proof of it. The original one, which is still probably the simplest way of proving it. Okay, so we're going to prove that on integers there exists such a measure, such a density. Yeah, it's a remarkable fact that one can define density for all subset of integers. Okay, density, so that it has this property that it's the density of the union is the sum of the densities. Density of the whole of all subset of all integers, it's 1, and moreover it's invariant under translations. Okay, so the density of the subset translated is the same as the density of the subset. What is interesting that we'll prove existence of this density without being able to write it explicitly. Okay, and it's well understood that this cannot be done. We can only prove existence of such a density. So it will be the proof will use the Hahn-Banach theorem for functional analysis, and maybe it's the most remarkable application of this theorem, that you can define the density for all subsets of integers. Okay, so we will, yes, as we said, we'll use Hahn-Banach theorem. So we're going to define actually the functional on all bounded functions of integers. Okay, let me denote it actually also mu, because then this measure mu will get by applying it to characteristic functions of the subset. Okay, so the measure of the subset A will be the characteristic function, this functional applied to the characteristic function of the subset. Okay. So I hope it's not confusing using the same letter for the functional and the measure. Okay. So of course, well, if mu is the functional, it will be finitely additive. Okay, and now what are other properties this functional should satisfy, so that the measure for the whole group would be equal to 1, and that it would be invariant under translations. Okay, so the measure of gamma should be equal to 1 translates into condition that this functional on constant functions it should be just the value of the function. Okay, so on constant functions, we defined its functional to be the value of the function. Now, in order to satisfy this condition of the invariance under translations, so let us consider the subspace in L infinity, which consists of functions minus the translations. Okay, so f is a bounded function. Okay, and gamma is any element in the group, and f sub gamma means that we translated the function f by this element gamma. Okay, and it should be linear subspace. So let us take all finite sums of such. Okay. Okay. So if this measure is invariant under translations, it imposes that this functional should be 0. Okay, on h. So mu h should be 0 for all functions which are in the subspace. Okay, if we have a functional on L infinity of z such that satisfies this condition and the condition that and that it's 0 on h, we get a measure which on the whole group is 1 and which is invariant under left translations. Okay, so that's how we defined that's how we define this functional to be constant on to be value of the functional constant functions, and to be 0 on H. Okay, one has to, it might seem obvious, but one should also check that you cannot get, you don't have constant functions in H. Okay, and then we want to extend it, to the whole L infinity. Okay, and you know that you can do it using Hahn-Banach theorem. Okay, so in order to extend mu to the whole L infinity of Z, you have to check that on that mu on defined in this way on constant functions and on H is bounded. Right? And being bounded is equivalent to proving the following property, that if you take any function in H, okay, so any function which is function minus its translation by an element in the group. And also, if you take a finite sum, actually, if you take the infimum of H of gamma over all elements in the group, the infimum, it will be non-negative. Okay? It might sound as something, well, completely trivial, okay, because if you have the function minus translation, you might think, yeah, it's obvious that it cannot be always greater or equal than 1, okay? However, till now, we haven't really used the fact that we're talking about integers, okay? This construction we could carry on if instead of Z, we had here arbitrary group gamma. Okay, and we know already that there are groups which are non-amenable. Okay, F2. So the first exercise in this class is to prove that this property, and this property, it's really equivalent to amenability. Okay, that this property is not true for F2. Okay, so for F2, try to find a bounded function, okay, and its translation such that difference, actually we have to use at least two functions like this, such that here you can get a function which is constant and equal to 1. Okay, and one can do it really using paradoxical decomposition. However, proving this for Z, it's easy, and I also leave it as an easy exercise for you. Okay, that if you have integers, you have a bounded function, you take its translation, you take the difference, and even if you take the finite sum, the infimum of such a function cannot be strictly positive. Okay, so that's the that's the proof of amenability of existence of such a measure for for integers, and it seems to me that it's still the easiest way of proving it. it used Hahn-Banach theorem, which is equivalent of to the axiom of choice, and actually amenability of integers using this definition of von Neumann is equivalent to some form of the axiom of choice. Okay. Maybe just a remark concerning this proof is that, well, already in case of integers, we call this measure density. So you might think that a way to define would be really to define this density of a subset A as the limit when you take the number of elements in A in the long interval, say from minus n to n. Okay, you count how many elements you have in this long interval. You divide it by the number of all elements in this long interval. So this is 2n plus 1, and you could take a limit when n tends to infinity. Okay, however, it's easy to see that for many subsets, this limit does not exist. Okay, and that's why we had to do this construction. And there is no uniqueness of such a measure by no means. So it's well, it's easy to see that, for instance, for any such a mean, the density of even integer is 1/2. Yeah, because if you translate them by 1, you get odd numbers, and the union is the whole is all integers. Okay. However, if you look just at natural numbers, okay, the density can be anything between 0 and 1. It can be 0, it can be 1, or anything in between. So there is no uniqueness. There is no uniqueness. Okay. Maybe another important remark is that if you do this exercise for integers, so let me maybe stress this is okay for integers, but you can you realize that the same proof works for all abelian groups. Okay, so for Z2, Z3, you can also prove this property, and therefore they are amenable. Okay, so all abelian groups are amenable. In particular, SO2, okay, so the group of rotations of the circle is amenable. Okay. Therefore, on S1 on the circle, there exists a measure defined, probability measure defined on all subsets, which is finitely additive and invariant under rotations. So there is no paradoxical decomposition of S1. Okay, so for S2, we've seen this decomposition. On the other hand, one cannot do it for S1, and because of existence of this measure, which cannot be described explicitly, but we've seen that it exists. Okay, so maybe we'll stop with the examples of amenable groups for a while. So we gained some intuition already. We know that abelian groups are amenable. So let us maybe move now to the side of non-amenable groups, and in particular, let us ask this question, whether there are non-amenable groups which do not contain F2, which do not contain a free subgroup. So this question was actually very led to deep developments in group theory. And let me write an example of a non-amenable group without F2. So let us consider so-called Burnside groups. Okay. In particular, well, B2N. So this is a group generated by two elements, A and B, and as relators, we'll put all words in letters A and B to the power n. Okay, so it's the presentation of this group, which means that this group is a quotient of a free group rank 2, okay, a group on letters, a free group on letters A, B, and the inverses, divided by the normal subgroup, by the smallest normal subgroup, which contains all such words. Okay, so it's called Burnside group because he asked the question about existence of groups, finitely generated groups, which are infinite, yet all elements are of finite order. Okay? In this group, any element to the power n is identity. Okay, and the question whether this group is infinite, it motivated a lot of developments in group theory in 20th century. Okay, and of course it's a good candidate also to, if it's infinite, to answer this question, because certainly doesn't contain F2. Okay, the question, so the question whether this group is finite is infinite, well, the answer depends on n, and it's still unknown exactly for which n's these groups are infinite. Okay, so it's an easy exercise that for n equal to 2, it's finite. You have to think for a while for n equal to 3, and it's also true for n equal to 4 and 6 that these groups are finite. Okay, for as far as results concerning exponent for which these groups are infinite, so still the best result is a theorem of Adyan-Novikov. So it's from 60s. Actually, so the first results were announced in the middle of 50s, but it took 10 years to write the proof. Actually, during the process of writing the proof, the exponent changed. So the theorem says that if n is odd and sufficiently large, this group is infinite. Okay, so it's still not known what happens for small n. In particular, it's open for n equal to 5 and n equal to 7. Okay, and I would say that for n equal to 7, everybody thinks it's infinite. For n equal to 5, it's not clear. Well, okay, and so the proof, which takes hundreds of pages, actually also one can reinterpret this proof that it's infinite to prove that it's non-amenable. Okay, so it's an example of an for n equal to 665, it's an example of a non-amenable group which doesn't contain F2. And historically, the first examples were obtained by Olshansky in 80s of non-amenable groups which do not contain F2. Okay, so this was an introduction to amenability. The following lectures, I'll give you other definitions of amenability. Actually, I'll give you a very simple definition of amenable groups from 50s. And at the time, actually, it was thought that with this definition, the subject was finished. Okay, it's such a simple condition that one could very easily check if the group is amenable or not. Okay, this is very abstract, especially with the proof we've seen from functional analysis. Next lecture, I'll give you very simple condition. So for a long time, it was thought that the theory of amenable groups is over, that one could understand everything about this group. However, in recent years, there were new constructions of amenable groups, and nowadays it seems that it's a very very large class of groups, and it seems difficult to give a simple characterization of these groups. So that's what we're going to learn in the following classes. Okay, thank you very much.